All right, let's get back to the material. Define material and modify and show. All right, so you said that's a metric system, right? Why we have a 4,000 pound per square inch while all my unit are in 1/4 meter? Focus. So this is just the name of the material. The name of the material. I can name it, as I said before, Omar, or whatever name that you want to say, or what I call it FCU. But everything here is in 1/4 meter. The weight per unit burden and the Young's modulus and everything here. So it is just a name. So you can name it whatever you want, but usually when we name it with, this is basically the conversion of the unit. Like if you change the unit here, everything here is gonna be changed. So the name doesn't matter much. You can name it any name, any unique name that you want. And then, but the things that matters here, that these units must match the general units that you are using. Okay. All right. So I'm gonna keep it the way it is, and then I'm gonna say okay. I'm gonna get back to define load patterns. And here I'm gonna keep the unit load 1 because I don't want to calculate the own weight of the structure. I want the SAP2000 to calculate the own weight of the slab and the beam system. However, I'm gonna add a live load. And the live load, I'm gonna make the on weight here 0 because I don't want SAP2000 to calculate the on weight 2 times. Because if you kept it 1, he's gonna calculate the on weight and put it in dead loads, and calculate the on weight and put it on in the live load. And then I'm gonna hit OK. So I define the loads. Let's go define the sections. I'm gonna define frame sections for the beams. So I'm gonna add a new property, and I'm gonna add concrete beams. And let's say I'm gonna make these concrete beams, I'm gonna name it B25 by 70 centimeter. And I'm gonna make the depths 0.7, and I'm gonna make this is 0.5, and I make sure that the material is 4,000 pound per square inch. Concrete, I'm gonna hit OK. If you want to define the columns, just in case if we're gonna make this as a 3D, you can add new property and you can add rectangle, and you can name this column C1, for example, 50 by 50 centimeter. And I make sure that I have this 0.5, and I have this one also 0.5, and I'm gonna hit OK. If you want to define, for example, another column, let's say I'm gonna add a copy of this one. I'm gonna change its name. I'm gonna name it C2. And for example, let's make it C2 25 by 80 centimeter. And I'm gonna make the depths, for example, 0.8, and this one 0.25. I'm gonna hit OK. So I defined all the cross sections, and I'm gonna hit OK. So right now I define the beams and the columns. Let's go to the slab. I'm gonna define section, and I'm gonna go to area section. And as I told you before, there's multiple area sections that you can choose from. You can choose shell, you can choose plate, you can choose a solid. Actually, they don't have the membrane. But anyway, I believe the membrane is gonna show up when we go inside. So let's add shell as we agreed before, and add new section. And here, yeah, here it shows the type of the shell that you want. Do you want shell thin or thick, plates thin or thick, or a membrane? So usually I'm gonna go with shell thin because that's what we use with flat slab system. If you have a foundation that are very thick, or the flat slab system is really thick, like more than 0.5 meter or something, I would go with shell thick. So I'm gonna make a slab system of 30 centimeter. And I make sure, by the way, if you name it slab 30 centimeter, you still have to change the membrane thickness and the bending thickness. So why you have to put 2 thicknesses? So basically, the shell is kind of a membrane and plate at the same time. Do you guys remember? There's a membrane that can take loads in a specific direction, and there's a plate that can take loads in a different direction. So we said that the plate can have bending moment that way, right? That's the plate. The membrane take moment out of plane, like the shear wall. Walls is coming that way, and the shear walls is resisting the walls that way. Okay. So right now I big shell. Shell has both the plate and the membrane. So basically, it's asking me what is the thickness of the slab that is effective in the membrane reaction? So like use the full thickness. And the membrane reaction act this that way, so the full thickness is working with. In bending, which is the blade action, I want also the full thickness. So basically, they are both the same. Okay. And I would choose the material. I'm gonna keep the material concrete. It's always the thickness, which is like if the wall, it's gonna be that one. If it's a slab, it's gonna be that one. The smallest thickness.
So then membrane is vertical.
The membrane is like you have the slab like this, it's like this. That's the wall.
That means you're saying it's gonna be 30 centimeters wide
30 centimeter thickness. Yeah, that one.
if we design a membrane, but we're gonna design a slab, so if the
Exactly. So usually these things is kind of like this software is deal with it as a matrix. Okay, like do you guys remember the degrees of freedom? The degrees of freedom for the plate and membrane were 12, but for the shell were 24. So basically, when you put the load on the plate, the loads are gonna move the degrees of freedom of the 12, but there's nothing coming that triggers the other 12. So it's gonna make the other ones the zeros, and the other ones is gonna have numbers. Okay, so that's exactly what happened inside when you use shell for a system that is gonna get only plate loads. Okay, all right. So think about it like, oh, we are using shell for just safe to be safe. So, because sometimes I told you, you have a wall, and the wall usually designed because that's the thing. What happens with walls? We design the wall to take loads in the strong direction. What is the strong direction of this wall? That way, right? This wall is like weak in that direction. You give it load that way, it's gonna bend that way. But it's a stiff in that way. You guys know that because the stiffness is much bigger in the moment of inertia, right? So that's what we do. But is this what happened? Like this wall is only gonna take load in this direction? No. There's some loads are gonna come in the other direction and make bending on the wall. So this wall is gonna bend that way and that way. That way, maybe when torsion happens, and it happens. So that's why when we have wall inside the system, it's better to make it chill because definitely this wall is gonna have a moment that way and a moment that way and maybe a moment that way. Okay.
slab is similar.
If what? No, it's gonna happen whatever because this only happens when you have a seismic load. All like if you don't have a seismic loads, all the loads is gonna go down. There is no bending that way and there's no bending that way. This wall is gonna act like all the loads are coming that way.
For a slab, we also have.
That's true. If you
Is
have
that why we're putting 0.3 for the membrane, or
that can happen. Well, we usually put it just like as an effective thickness of the slab. But the slab, if it's there's something is called rigid and flexible membrane. So usually when we assume a slab is a rigid, that means the slab cannot do this action. But if it's a flexible membrane, so it can make that action. And right now, the membrane is effective in that case. So that's why we always model the systems as shell, because they can take membrane and the bending load, or membrane and plate action. Okay, so getting back here to where we at, I'm gonna hit OK after putting the slab thickness. So right now, the only last member that I need to define is the wall section. So right now, I'm not gonna draw any wall. In the future, I will. In the 2D, I'm not drawing any wall, but I'm gonna define it here. And I'm gonna say it's a still shell thin, and I'm gonna say its wall, let's say 30 centimeter too. And I'm gonna also still keep this is at 30.3. And this is 0.3, and I'm gonna use the same material of the concrete. So I have all the sections, all the loads, and everything is defined. So right now is the moment where I need to draw everything. So you're gonna start by drawing the walls and drawing the columns and then draw the slab. But what I'm gonna do, I'm gonna draw the slab first because it's gonna help me to draw the walls and the columns much easier. So how I'm gonna draw the slab? I'm gonna draw the slab here. You can come to draw, and there's something here. It's called draw poly area, which is the slab, or draw rectangular area. It's still a slab, or quick draw an area. Let's see the difference. All these are outside here. You can use them here. I'm gonna go outside. I can click this one. And here, when I open this, is asking me what cross section that you want to use when you draw the slab 30 centimeter or something else, because you can choose between multiple things. So if you look here, you will find the wall, but right now I'm drawing a slab. So if you pick the one that has the poly area, so you have to draw the slab one point by point. Can you see? Like this and this. And once I'm done, I can escape. Let's draw it. Okay, let me try again. I don't know, somehow it didn't draw the slab. Okay, let's try the rectangle one. Okay, draw with rectangle. I don't know why it didn't draw with the other one. So this is one big slab system here. I just want to make sure that I didn't draw multiple slabs on top of each other. Oh, it says here one area. That means it's only one slab. When I select it down there, it says one area. So that's also one way to do it. Or I can delete this, and there's something it's called the quick draw. Quick draw, you have to be in the 2D, but the thing is you have to click on each one by one. Can you see what I'm doing? It draw a slab in each area, bounded by a grid system. Okay, the easiest way to do that, I want to tell you something. When we do finite element analysis, and that's what all the software, this is the method that all software is using. SAP2000, ETABS, any software, I believe most of the software out there, they are using the method of finite element. What is the method of finite element? What does it do? It's an empirical method. And what I mean by empirical, like let's say this is the slab system, and this slab system has a support here, and support here, and support here, and support here. And it has a bunch of loads. What's supposed to happen to this system when it has this load? It's supposed to have a deflection, it's supposed to have bending. So the finite element method, if you take this class, and I believe it's I believe Dr. Mahrabi teach this course. I'm not sure if you guys took it. So finite elements solve the structure at the point. Like if you have a joint here and a joint here and a joint here, so these joints is where the finite element make the solution. And then it takes the average of all the points to come up with an average bending moment. So the thing is, let's say finite element try to solve for the deflection here, and the deflection here, and the deflection here, and the deflection here. What is the deflection here? You have a hint. And here, 0 and 0. So basically, once you have the slab system, let's say this is 5 meter by 5 meter, and you make the mesh size of the slab one mesh, and this mesh or this slab is 5 meter by 5 meter. So basically, the finite element is going to solve for 0 deflection, and the deflection that you are going to get in the middle is going to be 0. So that is one of the, let's say, the drawbacks of finite element. That is empirical method that takes average based on the number of joints that you have. So if you want to make your solution better, you have to divide this into more elements. So basically, when you get the deflection here and the deflection here, it takes average, 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 and then you are going to show more deflection. If you want to make your solution better, you have to divide this into more elements. And the smaller the elements that you have, the more accurate is your solution. However, if you increase the number of elements massively, the software can take forever until solve, because it is going to take more time to solve at each joint. And then he needs to take the average of each one of these joints. You guys got that? So the acceptable mesh size when we do finite element analysis is around 0.5 meter. So that's what we mostly use when we solve for gravity loads. So what I'm going to do, I want to draw the whole slab system of the structure, and divide them in a way that I can get accurate solution. And this way is gonna be by making the mesh size equal to 0.5 meter. So let's see how we can do that. What I'm gonna do first, I'm gonna draw one slab for the whole structure. Oh, sorry. Oh, why didn't... Okay, make sure it's a slab 30 centimeter. And then I'm gonna stop it here. All right, so this is one slab. And then what I'm gonna do next, I'm gonna divide this slab with the grid system. I will go to edit, and then you will find something is called edit area and divide area. And then I'm gonna go to divide area based on points or area edges, and I'm gonna do it divide with the intersection of visible straight grid lines with the area edges. And I'm gonna say, okay. So why did I do that? I did that because if this is your slab system and you have a column in the middle, if you don't have an intersection of joints at this column, like let's say you have a column here, or let's say you have another column here, this column is not gonna feel the slab. The column need to be attached to a joint. If the column is not attached to a joint, the slab will never feel it because that is how the finite element is working. So I divided the slab system at the intersection of the grid lines because I know at each grid there's either a column or a wall. And I need this grid system to have a point at this column or the wall. Okay? If you try, when you go home, do the same thing and draw a column here, you will find that the slab having a deflection, like not feeling the column, like it's going up and down. So that's really, really important when we do finite element analysis. So let's say that you have a column here. What you should do, we usually drag this point and drag it here. Move it here. There's a way that we can do this on SAP2000. All right, so I did divided the slab system that way so I can draw hinges at the location of the column. So right now I can assign, like I know that there is columns at these four corners. I'm gonna select them. I think I had a column here. I didn't have column here. All right, I had one here.
If I drag and draw like a rectangle to select them, it also selects the slab area. Does that matter?
Yeah, actually, it's the joint in the slab. What we did here, like this division, this is a slab, and this is a slab. So basically, you generate a specific point on the slab that can drop the load at the column. If this joint, because the thing is, it's all about these joints. It doesn't matter what is inside here. It's all about these joints where all the calculations happen.
Like if I do this, select the points. And it selects this.
Yeah, that's not, it's oh, that's your question. So it doesn't matter because when we assign hinges only assign a joint.
Okay.
Okay, so oh yeah, I'm selecting here. Okay, you guys tell me if I missed anything. I believe that's all the columns that we had. Let's look at the plan. I had all columns around the core. And oh yeah, I don't have a column here because I have a wall on these sides. So maybe I would go back, take these out because I have walls at this areas. Okay, I'm gonna go here and I'm gonna add a sign joint.
I think you missed some.
Where?
So at the bottom, yeah, where the walls should be.
Here?
No, to the left.
Here?
Right, no, right, to the right, that one, take that one off, and then on the other
Oh
side.
yeah, because there is wall. Okay. By the way, if I left them, it's okay because we are gonna assign some stuff here later, and you're gonna find out. But let's keep it that way for now. I'm gonna assign, joint, restrain, and I'm gonna make hinges, and I'm gonna say okay. So right now we have hinges at this location. So what about the wall? The problem with the wall, if I want to model it, thing is the column is just at one point, but the wall is linear. So what I'm gonna do, I'm gonna make a beam like here, and I'm gonna make this beam really, really stiff. And add. Okay. Imagine with me that you have a wall here. If it's a column, the column is just holding at one point. But if it's a wall, it's holding the whole area. So this slab is feeling a very stiff element here, which is the wall, that have a. It's like imagine with me that the wall. Can you see this beam? It's just a 7.7 or 1 meter. 1 meter, for example. The wall is the whole story height. So that's what the slab is seeing. A very stiff beam that has a depth with the whole story height. So I can make a section and make the stiffness of this section infinity or very huge and assign hinges at every point of this section. And I'm gonna show you right now how we can do that. But let me make define a section, frame section, and let's say this frame section is the beam, the same beam, and I'm gonna add a copy. And I'm gonna name, let's name it F section 1, the same name that the software developed. And I'm gonna set modifier, and I can multiply these modifiers by like 10. Like I'm multiplying the stiffness of this beam by 10. And actually, let's actually not playing the weight or the mass. Let's keep the mass the same. Just playing in the stiffness. And I'm gonna say, okay. So why I did this section? Because right now I'm gonna draw a beam and I'm gonna pick up this section. And by the way, this section is temporary for now. And I'm gonna draw at the location of the walls. I'm gonna draw one here, and I'm gonna draw one here. This section is a beam section that is really, really stiff, and we are gonna find out how we can make this section act like a wall. All what I need from this is I want a reaction. Like I want a reaction at the supports that are here. And I believe I have a core here. Did I miss any walls? Oh, I had ones here. I think I got them all. All right. So that's all the walls that I have. And I'm not gonna assign supports right now on the wall because I'm gonna tell you why. But what I'm gonna do right now, I can run this model. I can put the loads. I can actually assign the supports at the end of this walls, and I can run the model. But the thing is, this model is not gonna be that accurate because can you imagine? This is the mesh size. Can you imagine how big it is? 5 by 5, bounded by a column. So you need more joints here to improve the accuracy. So you need to divide this into more small elements so that the software can calculate the deformation and calculate the bending moments and the shear force and everything as inside and increase the accuracy inside the slab. But you know what? Let's run this model without doing this and see what's gonna happen. Let's see how much time we have. Okay, I'm gonna assign supports here so that you can imagine what I'm talking about. And here. Assign, join. Did I miss one? Ah. Join, restrain. I'm gonna say okay. All right, so let's run this slab under its own wait, I didn't save the analysis. I'm not gonna run modal. And I'm gonna say run now. It's gonna ask me to save the analysis. So let's save it as slab 30 centimeter. I'm gonna say okay. It's not gonna take that much time when you run the analysis with respect to if you divided this into smaller mesh. So the analysis will be fast. And let's see how's the dead load, because right now this is slab, it's under its own weight, the dead load. So let's see how this is gonna look like. All right, I'm gonna show the deformed shape in the 3D. So let's say I wanna show the deformed shape and I wanna show the deformed shape under the dead load. And I'm gonna say, okay, look how the slab look like. It feels like a broken, not sure if you guys can see it. Can you see? It's like a broken in the middle and making like this, but this is not the actual deformation. The actual deformation should be like curved. You see? So that doesn't make sense. Why? Because basically he's taking an average between this and this. That's only one point in the middle that can move. And all the point is dragged. So the thing is we need to add more points so that we can make this shape more like realistic. So by the way, in the showing the deformation, you can show contours. Like you can say here, I want to draw contours in the Z direction because this is where the deformation is happening. And it's going to show you how's the contours look like. Where's the maximum deformation? By the way, the maximum deformation usually is around this area. But the thing is, this is not that much accurate because we didn't define the mesh in the right way. Okay. So let's see how we can improve the accuracy. I'm going to unlock the model and start dividing this into smaller mesh. So I'm going to select all the slab. I said Control A. When I said Control A, it selects everything. Slab, beams, frames, joints, everything. However, this doesn't matter right now because the loads or the things that I'm going to do is just specific for the slab. So I'm going to go to Edit and I say Edit Area. So basically, he's going to go, SAP2000 is going to go to my selection and select only the area and apply the order that I'm going to make only on the area sections that I have. And I'm going to divide the area. I'm going to tell SAP2000 that divide the area into objects of the maximum size, for example, 0.5 by 0.5. So SAP2000 is going to divide these areas into a maximum area of 0.5, 0.5 while maintaining the original division. Okay, so this doesn't mean that the areas is going to be 5.5. The maximum is going to be 5.5. But he's going to divide it within here. Let's say this is 4.7. So it's going to make, for example, the mesh size 0.4 or 0.3. Depends on how the areas look like. So, and then let's hit OK and see what's going to happen. All right, look what happened now. The mesh size is really small. And I still have a joint at each column. And I want to do something for you. Okay, let's actually zoom, restore the full view. I don't know what happened here. Okay. Yeah, I want to do something. I want to put a hinge somewhere here. Like I'm going to add a point. Let's click on the point here. And I'm going to add a point here. And I'm going to select this point. Let's select this point. And I'm going to assign a hinge at this point. Joint, restrain, and I'm going to put a hinge. All right. There's a hinge at a point that is not connected to the slab system. And see, let's see if the wall is gonna, if the slab is gonna feel this point or not. Okay, that's one thing. Other thing, I can put live load. But one thing we forgot to do, and I wished if we didn't forgot because right now it's messy a little bit. There's an elevator in this area, right? Should we have a slab here or no? If there's a slab here, there's no way that the elevator is gonna go up and down. So usually, we have to delete this thing. And usually we put a coupling beam here, like if we look at the drawing, there's a beam here. So let's put this beam because we forgot to draw this beam. So I'm gonna put, usually the coupling beam is much more heavier than the regular beam, but let's put beam 25 by this. So I put the beam and everything, and let's assign live load. I'm gonna select the whole slab system. And the thing is right now, the software only calculates the loads. Only calculates the own weight of the structure. However, there's weight that is not here, like for example, the flooring weight or the live load. So let's assign this. So I'm gonna hit assign, and I'm gonna assign something is called area loads. And this area loads is a uniform shell because all my loads are uniform on the whole square footage of the area. So I have a super dead load, which is the flooring load. So let's assume that the flooring load is 150 kilograms or 0.15 ton per meter square. And by the way, when I leave this load in the dead load, so basically it's gonna combine the flooring that I have with the own weight of the structure in the same dead load. If you want to separate them, you have to create a new load pattern. Let's call it super dead or something. But right now, I'm gonna keep it that way, and I'm gonna hit okay. And all right, let's select the slab again, and I'm gonna assign the live load. I'm gonna go to area loads, uniform shell. I'm gonna change this from dead to live, and I'm gonna make the live load is 200 kilograms or 0.2 ton. And I'm gonna hit okay. By the way, all the green that you have here, basically SAP2000 wrote 0.2 and each kilogram. 0.2, 0.2, 0.2. So that's why you have all this green. If you want to make sure of the loads that you put on your system, you can make zoom in view. Can you guys see? So he's writing the loads on this slab. The live load is 0 in the X, 0 in the Y, and negative 0.2 in the Z direction. You can right click on this shell, and you are going to find all the assignment on this shell. You can find the loads assignment. It has dead 0.15 and it has live load of 0.2 in the gravity direction. All right, so I have all the load. So let's run this slab and see what we're gonna have. So I'm gonna run the analysis and I'm gonna hit run. It's gonna take more time right now because we have more elements. Well, it didn't take that much. All right, the thing is, I can see the deformed shape right now, but there is a lot of stuff here that I don't want to show. So what I'm gonna do, you can click on this checkbox. Can you see this one? And I'm gonna ask SAP2000 only display sections. And general options. I'm not gonna show ages or reference lines. Let's say apply, see what's gonna happen. And I don't want to show the points because it's annoying. So I'm gonna let's put the restraints. Apply. Okay, I'm gonna say F4. All right, let's get back here. And I'm gonna go to the area. I'm gonna show fill objects. Okay. I just these joints showed because we had, okay, let me,
What are you trying to show?
hmm? The thing is I want to hide the points that are in the middle here. So I'm trying, oh yeah, let's make it invisible. Okay, here we go. I'm gonna click on this view too, and let's make it invisible. All right. Because it was like I can't see very well when the software was showing me everything. So let's see the deformed shape. I'm gonna make zoom into the full view. All right. Can you see now how's the deformed shape look like? A little bit heavy, but this is, can you see right now? You have more points, there's contours, and things are much more realistic and close to the real. Like you have here, this is the center of the slab system, where we have one of the biggest deformation. And let me actually close this view and get to that view. And actually you can play here with the visualization. Like for example, if you want to show general options and you want to show the sections, apply ages, like something like this, so that you can have more realistic view. And basically in this view, you can get closer to the maximum deflection and have your cruiser. And then you can check, like, for example, here's the maximum deflection is 0.0025. But by the way, this is only due to the dead load. If you want to check this, due to a combination, you can define load combination. For example, I can define combo 1. I'm going to multiply the dead load, for example, by 1.4 as a scale factor, and live load by 1.6, add, and you can visualize the deformation due to the combination of dead and live load. And I'm going to hit OK. So when you do this, you are going to have deflection here definitely much more. Which is 0.004, which is almost the double. I want to look for the column that I drew, and do you guys remember where it was? So that, because the thing is, I drew a column somewhere here. Okay, let's show the undeformed shape.
We don't look symmetrical. It's below the. It's going to get right there. You just pass from that, right?
This one?
Yeah.
Okay, let's zoom actually on this column and see what's gonna happen there. And let's show the deformed shape. And let's say, okay.
Oh, because it doesn't.
It like, if there's a column here, it should have a blue like this. But it doesn't. Like all the columns and all the support, it has blue here at that column. That means that the slab didn't feel it. And if we want to see this in like, let's remove the contour lines. Sorry, I'm gonna hit OK. And actually, let's remove the fill. Like I'm not. Let's go to the general options and get rid of that. Let's see if the column is there. Somehow we can see it when we run the analysis. It is not shown. Yeah, here. Yeah, so when you run the analysis, it doesn't show because it doesn't contribute to the slab system. So it's basically, it's like a dummy column that doesn't do anything to your system. All right, I want to teach you how to extract some results here. So I want to remove the slab. Let's make it by label. Let's remove the sections. And actually, let's remove the labels too. And I'm going to get back to the general options. Let's fill the objects. And you can see the slab something like this. I'm going to say I want to see the XY. If you want to see the 3D view, you can see the 3D view from here. By the way, if you want to show the slab as a thickness, you can come here and say that to the general option that you want to see an extruded view. Extruded view basically is going to show you how, but it's going to make the whole software is heavy. Like, can you see? It is. It's going to show you some thickness of the flat slabs and beam. And by the way, we forgot to put beam around the slab system. Like, we forgot to put it's called the marginal beam. If we want to put it, basically, you are going to come here to the beam section and you say that you want to draw the B 25 by 25 and you can start drawing your beam all around, something like that. And let's get to the 3D. And right now you can see your structure in a 3D visualization. You can run your analysis again. All right. So if you set the animation,
But how can it be? Wouldn't those be considered walls? Shouldn't they be?
okay, look at,
Shouldn't be affected.
what is your question again?
Why are the beams affecting them?
Here.
Aren't those
Or here.
supposed to be walls?
Which one?
Yeah,
This is the beam.
those are beams. Those are
Yeah, this is beam. It's called like when you have a building, a flat slab system, sometimes we put a marginal beam around the slab system. It's called marginal beam. But look at what happens here. Has deflection. Doesn't have any. Why? Because we put two supports and this is acting like a wall. We made it to act that way. How? We put two supports at the start and the end, and we make that beam very, very stiff. So you barely have deformation at that beam. But if you want to make this beam more acting like a wall, you pick all these joints and assign a hinge, like this joint and this joint and this joint, and assign hinges at all of them. So that's also another way. Like you can pick a flexible beam and put hinges at all the points on this beam. So this is multiple ways to do it. Okay, so that's it for now. Next time we're gonna see how we can extract the results like bending moment, shear force diagram, bending moment on the slab in the X and Y direction, and how we can convert this into a 10-story building. Okay, see you guys next time.
Sounds good.
Yeah, just 1 second. Let me shut that.
Thank you.
Thanks. Have a good day.
Bye, Professor. Thank you.
Thanks. Have a good day.